Blackness. There are few circumstances more terrifying than that of finding oneself completely and utterly in the dark. Around the world, millions of people open their eyes to complete blackness every day. Recent surveys show that total blindness affects over 39 million people globally, rendering them in many ways cut off from the world. Yet a recent breakthrough may, in the coming years, lead to technology which could bring many of them back into the light. In 2004, researchers discovered graphene, a substance with seemingly miraculous properties. Composed of a sheet of carbon 1 atom in thickness, graphene demonstrates attributes never before seen in any material. For example, a sheet of graphene about the thickness of aluminum foil can easily support a 2-ton weight, the mass of a fully grown African elephant. Of course, this assumes that the weight is spread around the sheet. An elephant is quite large after all. So the obvious question is, how much can we decrease the area of the weight before it punctures the graphene film? The answer is startling. Calculations have demonstrated that the 2-ton weight would need to be concentrated onto the tip of a pencil for the graphene to break. But graphene's strength isn't its only remarkable property. It's also one of the most conductive materials we know. It has potential to completely replace many modern electronic components. Additionally, graphene is extremely biocompatible. This means that our bodies are able to accept it through surgical operations with no major adverse health effects. The same cannot be said for the vast majority of synthetic materials. So to recap, graphene is really strong, really conductive, and it fits well into the human body. If only our bodies contained fragile electric circuits. In fact, they do. The human nervous system is essentially an electrical system. The way the brain communicates with the body is almost entirely through electrical signals, with neurons acting as conductors. With this in mind, look at this model of the human eye. Light rays which strike the eye's lens are concentrated at the retina, where they are transformed into electrical signals and relayed via the optic nerve to the brain. However, those who lack this key neural pathway can have no communication between their eyes and their brain, resulting in complete blindness. This form of blindness is known as retinopathy, and it is the most common form of severe visual impairment worldwide. To illustrate this, here is a simple circuit. Recall that the brain and its neurons are part of an electrical system, one which requires complete connection to function. Now imagine that this wire represents the neurons connecting the retina to the brain. In an unimpaired body, all the visual information flows straight through to the brain for processing. But remove this link, and you can see that there's no connection at all. The circuit is open. In this sense, the nervous system, despite being so complex, is binary, on or off, completely functional, or absolutely useless. The trouble is that in this circuit, I can just stick a piece of copper into the missing link to complete the connection, while in a human body, you have to consider all the adverse effects the bridge might have on the patient. A few years ago, researchers discovered a way to safely bridge the gap. They called it the Argus. Shown here on a model, the device is designed to be implanted into a living patient with retinopathy to restore their sight. It works like this. Initially, a camera held in front of a patient's face relays visual information it receives wirelessly to a receptor behind the damaged retinal layer. Then, the receptor must change the video into electrical pulses which the brain can understand. Though it requires extensive surgery, this has been shown to work in a number of patients today, effectively restoring their sight. However, this device may be just a first step in the development of solutions to blindness. Just last year, medical scientists in Germany discovered an even more direct and simple solution, one that may forever end the threat of retinopathy. In August 2014, researchers in Germany came to the conclusion that the gap could be bridged even more directly than the Argus device did, through the use of graphene. By surgically running graphene filaments through the damaged retinal layer, the dysfunctional neurons could essentially be replaced by the strongest and most conductive material on the planet. Because of graphene's unique strength and biocompatibility, no updates or changes to the device are necessary once it is implanted. Essentially, the patients are receiving a permanent prosthetic retina. Early tests have been successful. Researchers have since successfully integrated graphene filaments into a patient with retinopathy, effectively curing him of his condition. The result, graphene-based synthetic retinas, are likely to act for many as a cure to retinopathy in the coming years.
Perhaps the most remarkable thing about this new breakthrough is how flawlessly it combines two previously unrelated fields of science. It's probable that most new discoveries will be based on this simple idea: finding different concepts in different fields and just putting them together.
That, it can be hoped, is the future of the scientific method.